What is the most used man-made material on Earth? You guessed it, concrete. Look around, it's everywhere. Sidewalks, driveways, foundations, floors you stand on, and even entire buildings are made from concrete. So why don't we discuss it more? In each episode of Concrete Logic, we will explore one concrete-related topic with the help from industry professionals that are shaping the future of the trade. We'll talk with suppliers, contractors, architects, engineers, specialists, and even some proponents of competing materials about their views of concrete and their vision of its future. Hey, Concrete Logic podcast listeners. You are about to listen to the second part of my discussion with Paul Ramsburg of Sika, his history of concrete lesson. If you did not listen to the first part, the part one of it, stop right now. Don't listen to this. Go back, listen to that episode, and then come back and listen to this one. This is continuing that discussion. It's really good. Again, listen to the first one. You'll pick up a bunch of key moments in the history of concrete, and then we continue this conversation here. Thanks for listening, and let's get back into it.
We'll step back a little bit and back to the United States. In the early to mid 1800s, there's a boom in construction in the southeast U.S. Along the coast, and it's a type of concrete called tabby. When tabby's been around as a technology back to pre-colonial North Africa. And when enslaved peoples were brought from North Africa to the Caribbean, they brought this tabby technology with them. They're brought from the Caribbean to the southeast United States. They brought the technology with them. And in the 1830s, 1840s, there's a boom in construction of plantation houses made out of this. So what's tabby? It's oyster shells burnt to burn off the carbon. And what you're left with is a lime cement. And then they would mix it with sand and from the beaches, and then oyster shell pieces as coarse aggregate. And it was zero slump and to be packed into wooden forms. But it made an excellent concrete structure. Most of the structures built in the 1800s are still there, but despite hurricanes and tornadoes and several wars, Revolutionary War, Civil War, you can find cannonballs embedded in these houses because they didn't fracture. The oyster shells actually collapsed and kind of absorbed some of the impact of gunfire or cannon fire. But it's an interesting technology. But it had been around since tribal North Africa, is this concrete technology. But if you visit the southeast U.S., Florida, Jacksonville area has a ton of structures, or the Caribbean, Cuba, there's a bunch of forts and large homes still built out of tabby from the old days that are just as nice now as they were when they built them.
Huh. And they used some kind of formwork, you said?
Yeah, they would build a wooden form box. And usually the wooden box was 2 foot by 4 foot by 2 foot tall and had no top or bottom. It was just the sidewalls. And they'd put a box down. They'd hand pack the zero slump tabby into it, let it set for a few hours. Then they would remove the box and then move it over. And they basically built them the way you'd stack bricks, alternating 2 foot by 4 foot concrete blocks, but being packed or cast into place.
Gotcha. Huh.
So we're all the way up to the middle 1800s. There's a guy I think is fascinating from this era. His name is Thaddeus Hyatt in the U.S. And Thaddeus Hyatt rode with John Brown. You remember John Brown rode in what was called Bloody Kansas, and it was a bunch of Northeasterners who were abolitionists that rode to Kansas to fight against the slave trade. And Kansas was a big battleground state for whether it would be a slave state or a free state. And John Brown and his men were going in and violently freeing slaves there. And there was a little bit of a unofficial war happening at the time. And Thaddeus Hyatt rode with John Brown. And then he fought with the Pennsylvania Army in the Civil War. And he had a lot of victory there. And when the Civil War was done, he didn't know what to do with his life. So he invented and patented reinforced concrete floor slabs. He became a flooring contractor, is what he did after the Civil War. But the first patent for reinforced concrete floor slabs 1878.
Whoa.
That early.
And
What's he reinforcing it with? Well, it's not steel rebar, that's for sure. He's using various different metal materials. None of his design would work very well now, but it is an early form of metal being used to reinforce concrete.
so what do you use? I'm sorry.
So he was experimenting with various materials. Like he experimented with bronze, like bronze reinforcement. Why wouldn't bronze work? Think about that. The reason steel and concrete work together as a reinforcing system is they both have the same or very similar coefficient of thermal expansion. All materials expand and contract with temperature, and steel and concrete expand and contract about the same rate. But bronze is very different than concrete. So now you'd have concrete expanding and contracting in temperatures. Bronze is expanding and contracting at a different rate. So you had cracking and spalling because it was bad material. But he experimented with various metals. And he never really landed on steel rebar.
Yeah. Huh.
1887, the Frenchman Henri de Châtelet, who worked for Lafarge Cement Company at the time, figures out the compounds that make cement work. So we invented Portland cement. We did not know the mineral compounds that were in cement and what they did. For instance, tricalcium aluminate or dicalcium aluminate or tetracalcium aluminate ferrite. We know those compounds now and we know what they do. Châtelet is a guy that figured that out in the 1880s. And he named them A-light, B-light, and C-light. But now we go by the actual mineral compound name. But that helped us refine and create better Portland cements because now we could get rid of waste products that didn't need to be there. And we could focus just on the minerals that we were intending to put in there. So Thaddeus Hyatt in 1878 has that patent on reinforced concrete slabs. It's not much longer, 1889, that the Alvord Lake Bridge is built in San Francisco. It's in a park in San Francisco, and it's built with rebar. So here's one of the earliest instances of steel rebar concrete construction, 1889. And the bridge is still there, but people regard it as being a terrible idea. They think it's unnecessary. It's expensive. They don't know if it'll work or not. And it's kind of laughed off in the engineering community. There's a handful of other buildings in San Francisco that are also reinforced concrete. But then in 1906, just a few years later, you know what happens in San Francisco in 1906?
Is that fire?
The Great Earthquake.
Earthquake.
Yeah. The Great Earthquake of San Francisco, 1906. Guess what was still standing at the end of the earthquake? It was not the wooden structures. It was not the unreinforced concrete. It was the concrete that utilized rebar, still standing. So after that great earthquake of San Francisco, reinforced concrete takes off in the United States. So that every concrete now has rebar in it. And that's really what launched reinforced concrete construction, was that great earthquake in San Francisco.
Huh.
I like the people and the events that kind of got us to where we are in the industry. So we're in the late 1800s, 1891. First concrete street is cast in Bellefontaine, Ohio. It's Court Lane, still there. You can still drive on that concrete that they cast in 1891. Right around the turn of the last century, in the early 1900s, Thomas Edison gets involved with concrete. You might know Thomas Edison from his lesser inventions like the phonograph or light bulb, but he really perfected the cement kiln. Up until Edison, most cement was made in these large brick kilns that look a lot like, clay pottery kilns. There were people at the time that invented rotary kilns like we see today. They did not work very well. They weren't very long. They couldn't process very much material. They broke down all the time. There really wasn't a commercially viable cement kiln. Edison gets involved. He gathers patents the way Edison gathers patents. Either he's buying people off or he's sending his New Jersey goons to take care of them. But he gets a bunch of patents and then takes over. But he actually makes a working rotary cement kiln, the kind that we actually use today, a long line kiln. And he creates Edison Cement Works. One of the first American cement companies is Edison Cement Works. And Now he has a ton of cement. He's making more cement than the industry needs. And he needs to go out and figure out, how do I sell the cement that I got a ton of now? So he starts coming up with ideas. One of his ideas is concrete housing. And he cast 13 houses in New Jersey that are 100% concrete. He invents reusable steel molds in order to cast them. So now we see reusable molds for the first time being an Edison invention. And concrete housing is a great idea. He also had bad ideas, which is what I like about Edison, that he had a lot of bad ideas. He made concrete phonograph cabinets. Terrible. They sounded terrible. Some of them still exist. He partnered with the Lautner Piano Company in New Orleans for a year and a half. They made concrete pianos, like upright pianos. The soundboard inside was still wood, like the guts of the piano would be now, but the entire exterior was concrete. And his intention was concrete was cheap and wooden pianos were expensive. You could put a piano in every home if you could make a concrete piano. They were horrible. They were so bad, people just trashed them. Not one is in existence today. Because the records of the Lautner Piano Company, we have the design, we know how they're made, but no one can find a single one of these that survived. I guess they sounded that bad.
Huh.
But Edison's concrete house idea really took off. Gary, Indiana cast hundreds of Edison-style concrete houses as mill towns. And, the U.S. seemed to be taking to the idea of concrete homes early on. And then a guy that worked for Edison on the concrete house, cast-in-place concrete house project, was a guy named Grosvenor Atterbury. And he was a young man, but he branched off on his own. And he decided, casting them in place on site was difficult. We should make the concrete houses at a factory and drive them out there and put them together. He invented the precast concrete wall panel, and it was even insulated. We think of insulated precast wall panels as being a modern invention, but now you're looking at 1910, the first houses made with insulated precast wall panels were going up, and he delivered them on the backs of Model T Fords.
Oh, wow.
So a normal one-story house might have had 170 precast panels. So they're small panels, but he drove them all out there on this rig he had on a Model T Ford, and had small cranes erecting these concrete houses. Super popular idea that Atterbury had, and he built a bunch of houses in New Jersey and New York out of this. 1910, so the World War I happens, and France is destroyed. So Atterbury, who was actually breaking ground in the United States and making a lot of headway, he decides to go to France instead, because somebody got to rebuild the country of France after World War I. And they take to his building system very rapidly. It's a great way to build housing fast. So a lot of French homes built post World War I are built with the Atterbury precast insulated wall panel system. But because he went to France to do that, you see concrete housing taking off in France. Still today, concrete housing is very popular there. And it just kind of died out in the U.S. because it didn't have a champion like Atterbury champion the cause of concrete housing in the U.S.
Wow.
I always like to take a safety break. So in our discussion now, let's take a safety break. For the invention of the hard hat. I call this my Franz Kafka PPE break. Do you know who Franz Kafka is?
I have no idea.
He was a very famous surrealist author of the early 1900s. He wrote a book called Metamorphosis, probably the most popular work, where a guy turns into a cockroach. It's like a surreal story. You might have read, some people might have read him in college. But Kafka invents the hard hat in 1912 because his day job, he's an insurance adjuster, and they're doing a lot of payouts from people getting hit in the head in construction sites in Czech Republic is where he's from, Czechoslovakia. So he figures out this idea where he takes burlap and he coats it in like a tar and lets it harden, and he paints it, puts a little suspension system in it. And now for a construction company to have insurance through his company, they have to make sure everyone on the site wears these hardened hats, as he called them. So you have a surrealist author on a side job invents the hard hat. Interestingly, it was Hoover Dam that was the first construction site where the construction company required all their employees to wear hard hats. the first construction site where anyone walking on the site had to be in a hard hat and safety gear was Golden Gate Bridge. That's our little safety history right in the middle. Let's speed through some other inventions. 1913, the very first ready-mix concrete company. So until this point, you built the concrete plant at the site to cast there. The Coleman Company in Baltimore, Maryland in 1913 has the idea to shape a dump truck a little differently, alter it, and start delivering plastic concrete to the job site. Coleman Company is no longer in Baltimore, but they still do business in Ohio, the very first ready-mix company.
Wow.
Let's get to it. So early 1900s, we need to get to the career of Duff Abrams. If the Pantheon is the mascot of our industry, Duff Abrams is the patron saint of our industry. He's the third president of ACI. He defined the concept of fineness modulus. It's a measurement of how fine or coarse an aggregate, specifically sand, is. We use that in mixed design today. He defined the importance of water-cement ratio, and he promoted the use of water-cement ratio as the largest impactor to concrete durability and strength, both early and late strength. He did that in 1917. So we've known for well over 100 years that the guy with the water hose throwing extra water in the concrete truck is doing the wrong thing. We've known that for 100 years. It's been written down. Oh yeah, but think about that. 1917 is when water-cement ratio was defined. He promoted around this a little bit later than that. He promoted the use of the absolute volume mixed design method. He invents this. Before absolute volume mixed design method, people had a mixed design method called the 1-2-4 mix. That's 1 part cement, 2 parts sand, 4 parts stone. Add the water until it's the right slump. And a lot of early structures were built that way. The Panama Canal was built with a 1-2-4 mix. We think about that strength of a structure. It worked well in that project, but we actually come to mixed design methodology with Duff Abrams. He created the test method for workability of concrete. Do you know what the test method for workability of concrete is? That's we have an apparatus we called it. Originally was called the Abrams cone. Now we call it the slump cone. Right? He created the slump test right around 1902. We still run that test today, and it's not because it's a largely meaningful test. It's not because it's a super accurate test. I think we still run that because it's an easy test to run. Anybody could do it on any job site.
Not anybody. I've seen people screw it up.
Guys out there with a piece of rebar trying to rock the slump cone.
Or put it on. My favorite one was the guy was trying to do the slump test on the side of a hill.
Oh, that's on a hill. Or I've seen it on dirt, so they just don't have a base plate right on dirt.
Yeah, no base plate.
Yeah. So Duff Abrams told us the right way to do it 100 years ago. But this is the guy that wrote the very first edition of the manual Design and Control of Concrete Mixtures. We know that now is a manual published by the Portland Cement Association. They took it over, but Duff Abrams wrote the first edition of Design and Control of Concrete Mixtures. That's the concrete Bible. If you're into concrete mix design, you know that book in and out. And everyone has a copy of that in their office somewhere. Very important book in there. But he wrote the first version of that. And in the introduction paragraph to the very first version of that book, he coins the phrase mixed design. Before that, we would only refer to it as mixed proportioning because we thought of it as just the math. How does it proportion? But he goes on to explain what he means by mixed design. Mixed design is no longer just the proportioning of how things go together, but when we design a mix, we take in consideration cost and aesthetics and placeability, and everybody that has to interact with this concrete has a say in it. And that's a holistic design of concrete and not just proportioning of materials. But he coins that phrase in that book early on, and we gravitated to it now because everyone that has their hands on a yard of concrete should have a say in how it's designed. Right. And we all have a stake in making it successful.
Yeah.
Yeah. Duff is one of my favorite characters in the concrete history. Shortly after that, in 1914, the first commercially available fly ash is available in the U.S. In 1915, a guy named Lynn Mason Schofield invents color for concrete. You might recognize the name Schofield Pigments has been the largest pigment company in America for a long time. But Schofield starts his company in 1915 in Douglasville, Georgia, and it doesn't take off too well. He does a nice small business. He opens a second location and moves out to Hollywood, California, and he's doing okay out there. No one's really interested in color concrete. He's at a dinner party and he meets Groucho Marx, and he pitches the idea to Groucho Marx of pigmented concrete. Groucho Marx is all in, and he's building a mansion in Hollywood, and all the concrete in this mansion now is colored. His driveway, his pool deck, all the concrete, he's all in on pigmented concrete. And Groucho Marx has a dinner party where he invites over Schofield and Charlie Chaplin. Charlie Chaplin is so impressed with Groucho Marx colored concrete that he's building a bigger mansion, and he goes all in with pigmented concrete. Well, Schofield becomes like famous among the Hollywood crowd, and it all started with Groucho Marx. And that's when pigmented concrete, decorative concrete, took off in the United States, was largely because Groucho Marx had the idea that he liked colored concrete. But I love that he's at the beginning of that story.
Yeah. I don't know if we should like that or hate it.
1917, Australia decides to build all the railway system buildings out of total precast structures. So some of the early total precast structures happen in Australia. In the 1920s, the U.S. comes up with the airmail system. There's airmail flights from New York to L.A. And, before radar, the way you got around and flying is you looked over the side of the airplane. You looked out the window and you saw landmarks. Well, that's easy flying the East Coast. You could see lights of the cities. You could see mountains or ridges or lakes, and you flew by landmark. Well, when you get to the middle of the United States, there's a lot of land with no landmarks, right? We can look out the window now and see it all looks the same. So what did the U.S. Postal Service do to help their airmail pilots? They actually went and they cast concrete arrows on the ground from New York City to L.A. every 20 miles. I mean, they were large. They were 30-foot long, giant pointy arrows cast out of concrete on the ground across the entire landscape of America, stretching from New York to LA. Most of them aren't there. Development is taken away. But if you out in certain areas of the western states, there's still these concrete arrows setting on the ground that airmail pilots would just look out and follow the dotted line. We look at maps and cartoons where they make out like the dotted line was real. This dotted line was real.
That's real. Wonder who got that contract. That sounds like a good one.
Yeah, can you imagine? It wasn't too much longer after that the radars invented and flying instruments, and they didn't need them, but they utilized them for a number of years. That brings us to the 30s with the Hoover Dam. Everyone has Hoover Dam presentations. A lot happened with the Hoover Dam, 4 million yards of concrete, the invention of air entrainment agents. There's a lot that happens with this. I like to focus on one thing. There's a monument on top of the dam. You can visit it now. It's a terrazzo and concrete and marble monument. And it's a star map. And it's a monument dedicated to those who died making the dam. No one fell into the concrete in the Hoover Dam. That's the Boulder Dam. But in Hoover Dam, a lot of people fell from the canyon walls and died. It's a monument to them. But there's a star map there for the dedication of the dam. And the reason a star map is because the way the stars are mapped out, the universe will never be in that position, ever before, ever again. And there's a plaque there. Why would they do that? The plaque actually says when some civilization from another world finds this dam, they'll find the star map and know when it was dedicated and when humans were able to build such a monumental structure. That's how proud we were of the Hoover Dam, is we were certain it was going to outlast humanity. Mm-hmm. But to put a star map and that plaque there. But if you're ever visiting the Hoover Dam, I encourage you to go look for this kind of corner monument on top of the dam. It's very interesting. So that's the 30s. Let's jump up to World War II. I like to focus on the various powers fighting in World War II and what they decided to do with concrete. And in World War II, the United States built a concrete fleet. They built 14 ships out of concrete and down in Port of Tampa. Interestingly, they used the only admixture they used in the concrete was Sika plastimate. It's an admixture that's still available today. But Port of Tampa, they had 14 ships. Most steel is going to battleships or destroyers. So ships that were going to carry cargo from the U.S. to Great Britain were all made of concrete. And concrete, because it could be cast easier, it was a lot faster to make a concrete ship than it was to make a steel ship. And of course, utilize less steel. And these ships carried goods across the Atlantic. Out of the 14, only 9 survived. The rest were sunk by U-boats. But at the end of the war, they were brought back to Kip-the-Peak State Park, which is on the Delmarva Peninsula in Virginia. In fact, if you know where the Virginia Bridge Tunnel or the Chesapeake Bay Bridge Tunnel is, on the north side of that bridge tunnel, there's a little state park called Kip-the-Peak.
Yeah.
And I encourage you, if you're driving, you got to look at it. You pull in there and just right off the parking lot, there's 9 concrete ships which have been sank into position, and they're acting as breakwaters to protect the beach there. So this concrete served its country during the war, and it's serving the environment to preserve that state park now. But you can get a kayak and paddle around those old concrete ships. Very stunning pieces. Now, Germany used concrete in what they call flak towers. A flak tower is an anti-aircraft tower. And these large, massive concrete structures, sometimes 6 or 7 stories tall. The walls of these were about 5 foot thick of 8,000 psi concrete, and they had about 5 mats of rebar, 6 inch on center, number 5 bar. So you're describing like an impenetrable fortress. And the one in Berlin was especially impenetrable. In fact, when Berlin fell and the Nazis lost, the French, the Americans, and the Russians divided up kind of the area in Berlin. The French had this flak tower in their area first, and they shot at it with cannons and tanks for days and weeks, and they never put a scratch on the thing. They wanted to take the flak tower down because it was a sign of Nazi strength. Well, the U.S. Inherited it when they territory shifted. The U.S. stacked it full of dynamite and set it off. At the time, this is before Nagasaki and Hiroshima, but at the time it went off, it was the largest explosion ever in the world in human history. And it cracked the back wall. It didn't take the building down. It's like super strong concrete building. Nothing was taking it down. And you know how they got rid of this sign of Nazi strength? They buried it. They bulldozed all the material from the rubble from the city of Berlin, and they just piled it up on top of this. And still to this day, it's the tallest hill in Berlin. It is just this buried flak tower.
Whoa.
The British decided to use concrete in this way. You know, in World War I, they got pummeled by German airplanes dropping bombs, and they were totally unprepared for it. It wreaked havoc, and they thought never again. So what they did, they built parabolic sound mirrors. These are like concrete domes or bowls put on their side, and they would set a little guy up in the bowl, and if an airplane engine was coming across the channel, they could hear it coming miles and miles away before they could ever see it from these parabolic sound mirrors made out of concrete. And then they have early warning system. What's interesting is before they ever got the chance to use it, they invented radar. So there's hundreds of these parabolic sound mirrors, giant concrete bowls on the British coastline today that were never actually used during the war.
Mm.
The Russians were decimated by anti-tank weaponry from the Germans. So the way they utilized concrete is they covered their T-32 Soviet tanks with concrete. They cast concrete shell over top the tank. It made them impenetrable to the anti-tank weaponry. You couldn't stop the tank by shooting with anti-tank weaponry. The concrete absorbed that. But it was so heavy that it made them outmaneuverable. Like just humans could walk up to the tank and take it. You didn't actually need it. So bad idea in the long run, but they get points for effort. But in 1960s, the Soviets invent the first standardized precast concrete components, and they built a ton of housing because they need to expand housing. They're building entire cities out of precast concrete panel systems where they just cast a standard panel and then they can put them together in whatever means they need. 1967, a French-Canadian architect puts up a structure called Habitat 67. I encourage you to look at pictures of this. It's the most bizarre structure, but it's modular precast. It's a bunch of boxes stacked. It looks like it's defying gravity. But that starts modular precast. Well, now in the U.S., mostly modular precast, a little bit for housing, but mostly that's how we make our prison systems. And this building looks a lot like that size of modular structure. And I won't focus on a lot of buildings, but I got to focus on the Sydney Opera House. Everybody can visualize those big white sails that make up the Sydney Opera House. Those are precast concrete sails. The rest of the structure is concrete. There's 120 feet of parking garage under the water level. It's the deepest parking garage on earth is the Sydney Opera House, and that's all concrete that's holding back that the water there. But it's an impressive structure, concrete structure. 1980 sees the invention of self-consolidating concrete, which has become pretty common now. It happened in Japan and came to the U.S. later. Here's my favorite point. 1988, Paul Ramsburg cast his first concrete piece.
Yeah. Who's that guy?
In Midland, Virginia.
And what was that?
It was so it's an architectural barrier for the side of a road, and it's actually still there. The system's still there. It lines the Baltimore-Washington Parkway, which stretches from D.C. to BWI Airport. So if you're ever driving that stretch, look on either side of the road. It looks like a stone wall capped with like white stone cap, but it's actually a precast, architectural decorative precast concrete units. But yeah, 88, that was when I started. So early 2000s, the Burj Khalifa is cast. We know that as the tallest building in the world right now. It's a concrete building. It's a 100% concrete structure. That's not a steel building, the tallest building in the world. It won't be the tallest building very long. Saudi Arabia is building something called Kingdom Tower. It might be named differently later, but now they're calling it Kingdom Tower. It will be taller than the Burj. It's a concrete building. The 5 tallest buildings in the world right now are made out of concrete. Our structures soaring to new heights have surpassed what steel structures can do. So we've had to gravitate to concrete because we're well beyond what steel can do for our structures. Early 2000s, we see the invention of ultra high performance concrete. Now we're talking concretes at a 30,000 psi compressive strengths that have up to 4,000 flexural strength in a concrete. So we see structures like in Sherbrooke, Canada, there's a bridge, 60-foot span bridge that has no steel reinforcement in it at all. It's just the concrete. It's about 2 inches thick. 2-inch thick slab for 60-foot span with no reinforcement because it has such high flexural strength to ultra high performance concrete. 30,000 compressive. It's an interesting material. Early 2000s, it's invented. We just see it taking off now.
Yeah. So not in that bridge, there's nothing, no fiber, nothing.
So the material itself has some brass coated steel fibers in it.
Okay.
But there's no placed reinforcement, no pre-stressed strand, no rebar. It's just the fibers that are in the mixture.
Wow.
It's at the university in Sherbrooke. 2010s, 3D printed concrete becomes a thing. Mostly that is developed and perfected with the U.S. military, coming up with a way to how to erect barracks very quickly in Afghanistan. Just have a machine that could put down and 3D print a set of barracks in 24 hours and then take the machine away to do more. That's becoming commercially available now in the United States. Just this year, a group printed 10 houses in Austin, Texas, 900 square foot houses, one house every 24 hours. And they were Habitat for Humanity projects. So they're houses that will be given to people to live in. But some of the housing crisis that we're facing now in the country, one of the solutions being developed is 3D printed concrete housing.
Yep.
Now that brings us up to now, but I left out pre-stress. I love pre-stressed concrete. It's the niche part of the industry that I've had the most fun with. So let's focus just on pre-stress for a handful of slides. Pre-stressed concrete, when do we think that happened? The very first patent for pre-stressed concrete was taken out by a guy named Peter H. Jackson in New York City in 1858. Think about that. 1858 is before the Civil War. We have a patent for pre-stressed concrete. Now, there's evidence he made structures, no evidence that any of them survived because he did not understand the concepts of pre-stress. He didn't understand creep or shrinkage or any of the things we have to deal with. So nothing he made ever survived, but he did receive a patent for pre-stress in the 1850s in the United States. Some of his ideas got to an engineer named Eugene Freyssinet in France. 1886, Freyssinet really develops modern pre-stress theory. Freyssinet is probably the father of pre-stress. And in still late 1800s, he makes a series of bridges out of pre-stressed beams. And he's riding his bicycle over one of the bridges a couple years after it's made. And he notices there's a dip in the bridge. It's not a straight line anymore. And he contemplates it, and that's when he figures out creep. So then he makes adjustments to pre-stress stressing, how he has to over-design stress, over-stress, because there's creep and pre-stress. But all that gets figured out in the late 1800s, and really it becomes a full system at that time. Now, he's not stressing strand like we have now, 7-wire strand. He's stressing something that resembles piano wire.
Okay.
He comes up with the first chuck to hold the pre-stressed strands in 1826. So Freyssinet develops a lot. He has a student from Germany named Karl Maltner. And Maltner learns Freysinet's system, goes back to Germany, develops his own system. So the type of strand you use, how you stress it, when you cast, like the whole design of the structure. He comes up with his own system. During World War I, he receives the Iron Cross for fighting for Germany in World War I for bravery. World War II, before World War II starts, he's thrown in a concentration camp because he's Jewish. But he made a name for himself in pre-stress. Everyone in the world was taking interest in what Maltner was designing. And the British Secret Service understood what he had. And they sent Secret Service agents to Germany and broke Maltner out of a concentration camp, then purchased his family from a different camp and took them all back to England, where they supplied Maltner and set him up to further develop pre-stress theory and a pre-stress system. Well, Maltner spent all of World War II, while bombs are dropping in London, he spends the whole time casting pre-stress beams. He's not casting for a specific site. He has no idea what they're going to be used for. He's just making a bunch to perfect it. So he has all these pre-stress beams, the longest of which is probably only about 60 feet. So we're looking at short span beams. But after the war, London's decimated. It's destroyed. All the old stone bridges and wooden bridges they were relying on for infrastructure were down and gone. What did they have? They had a whole bunch of pre-stressed bridge beams setting in a pre-stress yard in London. They literally rebuilt London's infrastructures, trains and autoways with pre-stressed beams that Maltner had spent the entire war putting up. So the Maltner system becomes the most popular system. He outshines Freyssinet. The business he started in 1939 as a commercial business was the London Pre-Stressed Concrete Company. Then back in Germany in 39, there's a German engineer, Edward Hoyer. He develops the long line stressing bed. So up to this point, one piece had one form. Hoyer develops a very long stressing bed where you can cast multiple pieces in the same bed. And of course, they all have their own system for what cable they're using and how to retain the cable, how to stress. Back in England in 42, Maltner starts the rail tie pre-stress company, where he comes up with making railroad ties out of pre-stressed concrete. And he casts thousands of these. There are still thousands and thousands of pre-stressed railroad ties from the 40s that are still in use in England that Maltner himself made in the 40s. Now that system gets to a professor, and pre-stress is not taking off as a worldwide building material because there's a lot of concrete nerds that are developing these amazing systems, and they had no idea how to talk to anyone about it. They had no idea how to educate new people about it. It just wasn't disseminating to the industry until Professor Gustav Mengel gets a hold of it. And Mengel is a great speaker, and he's a great writer, and he writes the first manual on pre-stress. He goes on a speaking tour throughout the entire world, telling everyone about pre-stress that'll listen. And it starts to take off. Well, Mengel has his own system of retaining cable and the type of cable you use and design. Is not really a perfect system, but he's an excellent guy to get the world to take notice of pre-stress. And then in 45, two gentlemen, Guilford and Udall, come up with the Guilford-Udall system for pre-stressing. That's what we use now. If you picture the pre-stress chuck of the multiple jaws in a chamber, the 7-wire strand, we pull everything we do now is the good old Guilford system from 1945. And Mango immediately drops his system. Maltner drops his system. They all drop their own systems. They know this is the perfect system. So they all latch onto it. And then Mango comes to the United States in 1950, and he oversees the casting of the very first pre-stressed bridge in the U.S., and that's the Walnut Lane Bridge in Philadelphia. That's the first pre-stress in the U.S. in 1950. And that bridge stayed up until just a few years ago. They took it down because Walnut Lane was being expanded, and they needed to raise the bridge height. So they replaced it with a new pre-stressed bridge. It's still pre-stressed, not the original. But, that brings pre-stress to the U.S. And, the rest of it's easily discovered history. But I like to end on that. But what I like to ask people, though, we look at structures that the Romans made, like the Pantheon, and a beautiful, like defect-free concrete dome that's 2,000 years old, and we compare it to that sidewalk down at the shopping center cast 2 years ago that has pop-offs from freeze-thaw and cracking and stuff. Like, what's the difference? They didn't have better technology than us. Our materials are better. The difference is workmanship.
Yeah.
Like, really, the only difference between an amazing 2,000-year-old structure and the sidewalk that's falling apart is workmanship.
Yeah.
Whether it's the engineer or the contractor or the guy floating the concrete or the guy making the mix design, that's it. That's what separates bad concrete from good concrete. It's just workmanship.
Yeah. No wet cure.
That's right.
Man. Well, I have literally, I'm counting all my pages here. 1, 2, 3, almost 4 pages of notes.
Excellent.
So I learned a ton. And again, I really appreciate you coming on today. This might be 2 episodes. I think I'm going to break it up.
There you go.
So
Part 1, Part 2.
Part 1, Part 2, maybe Part 3. We'll see. But if folks want to reach out to you, maybe get you to do this presentation for them in person or learn more about Sika, what's the best way?
Yeah, I tell you what, why don't you send an email to me? It's ramsburg.paul at us.sika.com. We can include that somewhere in there so you can have that.
Yeah, I'll get it.
Feel free to email me anytime.
All right. Well, Paul, I appreciate it, and hope to get you. I think we have one other topic we wanted to maybe explore in the future together.
We wanted to focus a little bit on the details of ultra high performance concrete.
That's right. Yep. But appreciate you, and we'll catch up the next time.
Great. Thanks, Seth.
Thanks. Thank you for listening to another episode of the Concrete Logic Podcast. If you like what you heard and you think others would get some kind of value out of this podcast, please share it with them. If you have any ideas or topics that you'd like us to discuss on the Concrete Logic Podcast, you can email me at seth@concretelogicpodcast.com or hit me up on LinkedIn. Pretty active there. Again, thanks for listening, and we'll see you next time.